Hello, my name is Lorcan, and my teammate is Juan Enterria. This is our structure. It is a structure with a hinge, a spring, a temperature gradient, and it is supported by two pins, one at A and one at D. The three parts have the same length, 4 meters. It is made with steel S235, a square profile, and this steel has this temperature expansion coefficient, this elastic modulus, the profile has this inertia, and then the spring has this rigidity, and we have a force at B, force P of 5 kilonewtons. The temperature gradient is 400. Therefore, the maximum temperature on this side, the positive side, is 10 degrees, and on this side it would be 20 degrees less, minus 10 degrees. Therefore, the reactions that we have are, first, a horizontal reaction at A, AX. Then a vertical reaction at A, AY. Then a vertical reaction at D, DY, and a horizontal reaction at D, DX. Lastly, we have the reaction on the spring, which is CX. The indeterminacy degree has a special thing. Here we have a hinge on both sides. Therefore, we know that there will be no vertical force at A, no vertical reaction. Therefore, this is the same as if we have a roller here. With only AX, because the hinge will not transmit a moment. Therefore, ID equals the exterior ID, the external ID, because it is an open structure, and this is reactions minus equations, taking into account that this reaction is 0. Therefore, 1, 2, 3, 4. And we have 3 equilibrium equations. 1. So this means that this statically indeterminate structure. And this one means that we have one redundant force. We are going to consider our redundant force, the reaction of the spring. For this, we have to change our system into this system. With the temperature gradient as well, the point force, and both pins. However, this is separated, and we have x1, the redundant force, and here the other side. X1 as well. Now, we have that the relative displacement at C, which is delta 1 as well, or x1 is applied, is equal to the real displacement plus the virtual displacement. And we know that this relative displacement is equal to 0. Therefore, delta 1, 0 plus delta 1, 1 by x1 equals 0. And substituting, x1 equals minus delta 1 0 divided by delta 1 1. Now, we have to create two different systems, the virtual and the real one. System 0 is when the external loading is applied. So our system is this, the same as before, with our temperature and our point load, and we have to calculate the reactions. Here I forgot to say that this is our statically determinate system with 3 reactions and 3 equations. Here we have dx, dy, and ax. Now we have to get the diagrams. But first we need the reactions. If we calculate the sum of moments at point D, which is equal 0, we get that force P by distance L has to equal reaction AX by distance L. Therefore, AX equals P. Now, the forces in X have to be 0. So, dx equals minus AX, which equals minus P. Finally, the forces in Y have to be 0. So, dy equals P, because they have opposite signs. Now the diagrams. Axial diagram. There is compression. This AX is P. Therefore, compression, it is negative, minus P. Here we have P as well, compressing, so seen from the right, it is also minus P. And at the bottom, dx is minus P as well, so it is also under compression. And we get this graph. Shear force. We have that this is our system, and we have this compression turning into shear force here. So from left to right, it goes like this, P. And at the bottom, the same thing. This compression pushes down and the reaction pushes back up. So now our movement diagram is here. From left to right, it is positive. Therefore, it goes down. This is P by L. And the sign is like this. The superior fibers are in tension. There is no hinge, so it transmits the moment. And as we can see here, this is negative, so it grows. And this is the same. P by L as well at this point. Now we have system 1. Applying our virtual force x1 equals 1, unitary. Therefore, this is our system. Same reactions as before. AX, dy, and dx. And they can be calculated as at D, the moment has to be, and this force, 1. x1 equals 1. At D, the moments have to be 0. Therefore, the only force acting as a moment on this point is this one. So AX equals 0. The horizontal forces have to be 0. Therefore, dx equals 0. And the vertical forces have to be 0. Sorry, dx has to be the opposite of this one. Therefore, it is -1. And finally, the vertical forces do have to be 0, and there are no vertical forces except dy. Therefore, dy equals 0. We get very easy diagrams in this case. Here we have compression. Of value 1, -1 because of this compression. And then both the shear and the moments diagram are null for both. Now we have to apply the principle of virtual works. This is the general formula. With the actual forces, which we can see they're 0 because this for us is infinite. This K is the influence of the temperature. This is the influence of the shear forces. And this is the influence of the springs. In our cases, delta 1, 0 for the real system is like this. Taking into account the influence of the spring and the temperature. However, since we have to multiply by this diagram, which is 0, we obtain a result of 0. On the other hand, delta 1, 1 for the virtual system has a very similar formula. without K0 because there is no temperature. And again, this is 0 because this moments diagram is 0. Therefore, we get that the reaction is 0, which we didn't expect. Now that we have calculated this reaction, we can know our real determinate system, which can be calculated as m0 plus m1 by x1 for the moments, n equals m0 plus n1 by x1, and v for the shear, v0 plus v1 by x1. However, since x1 is 0 for all of them, we get that they are all equal to our original system 0, which would be this one. So this is our total system.
Okay, now we will do the second part of the exercise. We will calculate the vertical displacement of point B. For that, we're going to use the unit load method based on the principle of virtual works. To calculate the vertical displacement of B, we start with the same structure. But the determinate system. Therefore, we don't have anything at C. Since this is the unit load method, we need to apply a unitary force at B in the direction of the displacement that we want to calculate. The value of the force is 1 newtons. And we need to calculate the reactions as always. AX, dx, and dy. Just applying the equilibrium equations, we can see that in the vertical direction 1 and dy, it means dy equals 1. Applying the equilibrium of moments at point D, we have 1 times L in this side and AX times L to the other side. Therefore, AX has the same value, 1. And finally, if AX is 1, dx is minus 1 from the equilibrium of the horizontal forces. With that, we can calculate, or we can draw the diagram of axial forces, shear forces, and moment. This system, we can call it virtual system, so it's N virtual. From the structure, we start with a compression, which value is 1. Then we have another compression, and finally more compression. The value is always 1. Shear. Same structure. And this is very similar to the previous case for S0, when we had P here. So from here, from this, in this part, from A to B, this part of the structure, there's no shear force. And afterwards, we have a shear force that if we look like this, it's upwards. In the left, we have a vertical or positive vertical force, and on the right, a negative vertical force. And in the bottom part from C to D, we can call it negative, but the force in the left are downwards, and the force in the right heads up. And with this shear diagram, we can calculate the moment diagram, which is the more important one, and it will help us to calculate the displacement. From A to B, there's no moment, and from B to C, we have this shear force that has been drawn, taking it from this side to this side. Therefore, this is a free end, it must be 0, the slope is like this, and the value is the force times the distance. Therefore, 1 times L. And the fibers which are in tensions are the ones in this side of the structure. Here the moment is conserved, and since it is a free end and the slope is the same, we have once again the same triangle. The value of the height is 1 times L. The fibers that are in tensions are below. Once we have the moment diagram, we can start to calculate the displacement. As we have said, we use the principle of virtual works, which says that the external work is the same as the internal work. The external work is the product of the forces and the displacement, since the unitary force is 1 and the displacement that we want to calculate, By, vertical displacement at B. And the internal force, the internal work, is, as we have said before, takes account the normal force, the shear force, and the moments. But since we are taking an axial rigidity as infinite, and for shear as well, we only take into account the moments. Therefore, this is the integral of the product of our virtual moments, which is this case, times or multiplied by the real system, which is equals to m0, calculated in the previous section, divided by the modulus of Young and inertia, plus K0. K0 is the curvature produced by a temperature rise or a temperature increase in the structure. Here in our structure we have a linear increment which is positive this side and negative in this side. The value of the gradient is 2 times T, because it's T on this side and T on this side, divided by H, the height of the beam or the bar, multiplied by the expansion coefficient of the steel, and this gives us a value of 4.8 times 10 to the minus 3 meters to the minus 1. And with this we can solve this integral using the tables of the virtual of the moment diagrams. Therefore we start with the side. Here we have a virtual triangle, length L, height L as well, with this orientation, and a real system which has also shape L and height P times L divided by EI, also with the same orientation. Then we have to take account the curvature due to temperature. Virtual system again, L and the temperature. The temperature is a positive increment in this side and a negative increment in this side. This means this will expand and this will contract. As you can see, the curvature is in the opposite direction, like this. So this product will give us a negative value here. And again, the final part of the structure, we have our vector system, length L, height L, times the real system, length L, the same orientation, and height P times L divided by E and Y. Using the equations from the tables, we get that this is 1/3 the length times both heights, then is L times PL divided by EI, plus, this is not plus, it's minus because they are opposite orientations, and is 1/2 the length times both heights, so this is K0, the height, the gradient, plus, once again, 1/3 the length and both heights. This term and these terms are the same, so 2/3 LQ Y minus 1/2 L squared K0. Substitution with the values, we have 2/3 for cube, P is 5 kilonewtons, so it's 5,000 newtons, divided by 2.1 to the power of 11, and multiplied by 2.3 to the power of -7, because it's in meters to the fourth, minus 1/2 of 4 squared times 4.8 to the -3, which is the temperature gradient. If we compute this calculation, we get approximately a value of 2.4 meters of displacement with downward direction. This means point B will end up approximately here. It is a very big displacement since we have a 2-hinge bar in this side, and the force will act taking this bar up to here. Regarding CESPLA gives us a value higher, about 3 and 4 meters. The reason for this difference in the values is the fact that we only take in account moments. For us, the axial force and the virtual force do not create any displacement, since the longitudinal shear modulus are infinite. Therefore, we can say that this approximation is good and take this value as a displacement in B.